questions, just raise your hand. I will not share anymore, but go on, Pablo. Thank you very much for being here.
Thank you very much. So I'm super happy to be here in Buenos Aires. And also, probably will know Paco Cobreros. There is a very, very funded TV show in the 90s. Paco Cobreros that, you know, I came to talk about my book. So he was waiting, all the people were discussing. At some point, we start, you know, and say, I came to talk about my book. It was super fun.
So actually, I came to talk about my book, and to this, I think this is not working. There we go. Okay. So the motivation for this book is that, well, I noticed that there is a growing community of Spanish-speaker logicians. I think it would be nice if, as a book for undergrads or first years PhD students, to have a textbook that they can use in their own language. And the topic that gives unity to the book is the use of Smalian trees, also known as Tableaux or analytic trees. And one of the goals is showing that these trees can be used for many purposes, and you can use these trees to actually to extract like a proof theory out of a semantic theory. So let me give you a general overview of Tableaux. So the idea is that you depart from a semantic characterization of a logic. So the idea is that an argument is valid when there are no counterexamples, which means that all the premises take a value among the good values, let's say, and all the conclusions take a value among the bad values, okay? So you depart from a semantic characterization of logical consequence, and a tree proof will depart. So the initial ingredient of a tree proof is an initial list, right? So this initial list will record the idea that actually there is a counterexample to the argument, and you can decorate the tree with, well, usually you will have formulas, but you can also have symbols here or tags here or some decoration, right? Like recording that you are looking for the appropriate counterexample. The second component of a tree proof is the tree rules. The tree rules allow us to extend the tree by chopping the initial list into smaller pieces. And this chopping process is actually quite essential to the method, because it what makes it analytic, in the sense that you analyze, so these tree rules analyze the conditions that the formulas must have, the conditions that the component formulas must fulfill in order for the formula to have the appropriate truth value, right? And the chopping process guarantees that the search is always works in the direction of formulas of lower complexity, so that in the propositional case, you will get a decidable. So actually, tree proofs gives you not only proof theory, but a method of decision, right? So that if the argument is not valid, you will chop all the tree into the smaller possible bits, right? Okay, in the chopping process, a branch can tell you that a situation is forbidden by the semantics. And this is, in that case, we say that this branch is closed, right? In that case, the branch is telling you that you won't find the counterexample that way. So you keep chopping the initial list of formulas. Some formulas will branch, and in some branch, you can find a situation that is forbidden by the semantics. In that case, the tree is telling you, well, I'm trying to look for a counterexample for your argument, but you won't find it this way. So try the other ways. And that's why the third element of a tree proof is the closing condition. So you must specify when the branch is showing you a situation forbidden by the semantics. If every branch closes, then the tree is telling you that no counterexample can be produced for the argument, and so the argument is valid. So we have initial list, assume that there is a counterexample, three rules, chop your initial list into smaller formulas, and closing conditions. Detect the situations forbidden by the semantics. And we'll see in this course that actually you can like tune your initial list or the kind of items that you can have in your trees. You can have different rules for chopping these formulas into smaller pieces, and you can have different closing conditions. And by like playing with all these conditions, what you get is adequate tableaux for different kind of logics. So this is what the contents of the book. So chapters 1 and 2 talk about the classical trees. The chapters 3, 4, and 5 talk about the liar paradox as a motivation for the strong clean semantics and the strong clean logics STTS, LP, and K3, and also how to deal with meta-inferences in strong clean logics, only for STTS, K3, and LP. Although you can generalize, of course, these two other combinations of tags. Chapters 6 and 7 cover modal semantics and normal model logics, and the last part of the book makes something a bit more exotic, which is talks about supervaluationism in the context of vagueness, and develops what I take to be the adequate way to understand validity for meta-inferences. So this is roughly what I'm going to talk about in this course. Okay, so let's go to the classical trees. So as a way of motivation, this is very broad and very rough, okay? But you can motivate like the semantic point of view for a logic out of a realist position. So the idea is that for the realist, reality or substantial parts of it have an existence that is independent of the mind. That's why it is kind of natural for the realist to understand meaning in terms of representation. So the important thing of a theory of meaning is the reality that is somehow involved in or pointed out by our expressions. In the case of truth, the natural way of understanding truth from a realist position is a way of correspondence. So you have propositions, you have an independent reality, and truth means some sort of matching between these. And in the case of logic, let's say, reasonable for a realist point of view is the semantic point of view, where you talk about the extension of a singular term, or sorry, reference for singular terms, extensions for predicates, etc. While the proof theory is more naturally connected with anti-realism, right? So if reality or substantial portions of it are not independent of our mind, then meaning cannot be something like representing bits of reality, but rather based on how propositions relate to one another. So this roughly motivates an inferentialist view about meaning. In the case of truth, well, since there is no reality that is independent of our mind and can be one of the parts of the correspondence relation, it is reasonable to understand truth as a form of, let's say, coherence. And also in the case of logic, it is more natural to understand logic as a set of rules that allow us to construct proofs, right? So a proof theory. Now, of course, semantics and proof theory are very complementary. And I think it is, in a sense, Tableaux give you like a unified point of view between semantics and proof theory. So Tableaux are usually regarded much more as semantics, But actually, with the tableaux, you can, out of a semantics, extract a set of rules that work in a very formal way. And well, they are complementary in the sense that an argument is valid from a semantic perspective means that no interpretation is a counterexample. That an argument is valid in a proof theoretic sense means that there is a proof. Now, these views are complementary in the sense that if an argument turns out to be valid, it is in general more easy to prove an existential claim than a universal claim. So in the existential claim, you have just to point out to a particular proof. So if an argument is valid, generally speaking, it's gonna be easier to take like a proof theoretic stance to it. While if an argument is valid, since that, if an argument is invalid, it's gonna be somehow easier to try to produce a counterexample. So that's why these 2 points of view are complementary. Okay, so let's go for the classical trees. So in classical logic, we are going to talk all the time about propositional languages. So in classical logic, an interpretation is a function. Sorry, this is a typo. So it's a function from variables to the set of two truth values with conjunction, disjunction, and negation defined in the usual way. So a conjunction takes value 1 just in case both members of the conjunction do, etc. And an argument is valid, is classically valid, just in case there is an assignment of truth values to the propositional variables that make all the premises value 1 and all the conclusions value 0, right? So I said there is no interpretation that makes all the premises 1 and all the conclusions 0. So the initial list for a tree in the classical case is going to be a set of formulas where we write all the premises and then we write all the conclusions. And here it's a small trick, but it's a nice trick. Instead of using tags saying these ones must take value 1 and these ones must take value 0, what you make is just use the negation so that these ones should take value 1, these ones should also take value 1, but because of negation, it's like saying that these ones should take value 0, right? So this way you don't have to add rules for negated for truth tags and false tags, etc. Okay. The three rules are as expected. So a conditional is false exactly when the antecedent is true and the consequent is false. That's why it's a non-branching rule. A conditional takes value 1 when either the antecedent takes value 0. That's why we write negated A, or the consequent takes value 1, and this or is what motivates the branching rule. And the closing conditions are simple. So a branch will close when you have a formula and its negation. So for example, here is a classical tree showing that the conditional is transitive in classical logic. So we list the two premises, we add the conclusion with a negation, and then we start to chop things into smaller pieces. So this A and negation C comes from here. Then this negation A comes from the first premise. And since we have A here and negation A, then we mark this road as closed. This B comes from the first premise. And then we unfold the second premise into this. And we have B and negation B, so this branch closes. We have here negation C and C, so the branch closes. So easy and nice. Now, what happens when a tree doesn't close? Well, the nice thing is that here in the propositional case, the chopping process will terminate at some point. So in this particular example, we have a branch that is open. So this branch here contains all the information you need to produce a counterexample to the arrow. So basically, you select the open branch, and then for any variable, if that variable appears in the branch, then you assign to the variable value 1. If the negation of a variable appears in the branch, then you assign to that variable value 0. Okay? So the nice thing is that the open branch will tell you how to find a counterexample. So let's move to the strong clean trees. So we know from work of mathematical logic during the 20th century that any theory capable of some arithmetic is such that if you can express a concept, so if you have a formula with a single free variable, then there is a sentence that, so the theory can prove that there is a sentence that is equivalent to this concept applies to the code of that sentence. So informally, you can find a sentence saying, I am this concept, or I implement this concept. So this means in particular that for any theory, so means in particular that if a theory had a formula which is true exactly of the true sentences of the theory, we will have a sentence that says of itself, informally speaking, says of itself that is not true, right? So we can produce like a formal analog of the liar paradox. And that's why classically, this is Tarski's theorem. So classically, you cannot express the concept of truth for a rich enough arithmetic theory. And this, together with some seemingly uncontroversial principles about truth, which are the capture and release, sometimes called, or transparency of truth, you will have that the theory proves this, which in classical logic is pretty bad, right? And it looks like it is impossible to hold that lambda is equivalent to negation lambda if you have only two truth values, right? So this motivates expanding our semantics a little bit and saying that this time an interpretation is going to be a function from the variables of the language to three truth values, 1, 1/2, and 0. So super easy. Now you have, once you expand your semantics with a third truth value, there are several options on how to read the connectives. And in the book, and here we take the strong clean scheme, which basically tells you that conjunction takes the minimum value, disjunction takes the maximum, the negation flips 1 to 0, 0 to 1, and the middle value to itself. And we will read the conditional in the material way. So a conditional is equivalent to the disjunction of the negation of the antecedent and the constant. We will say that a formula is strictly true when it takes value 1 and is tolerantly true when it takes value non-zero. So if you have questions, please go ahead.
Yeah, you're strictly true or tolerant true, but so you don't use the terminology of like determinate.
You mean as a part of the language? I don't need to. I don't need to. So you will see how to. So actually,
Not strictly true, but
yeah. But usually one strategy when you have more truth values, so one strategy to develop your trees is like selecting tags for each truth value. Normally, this will give you a more complex tree rules, like with several branches. So a good strategy is like, instead of selecting tags for each truth value, select tags for sets of truth value. So here we have, so strictly true is the set containing 1, tolerantly true is the set containing 1 or 1/2. And with this, you can make at least what I'm trying to do here on all the tricks. Yep. This one.
So in the previous slides, you described the Tableaux methods. Is there something in the book about Tableaux methods, like proofs of decidability based on Tableaux?
Sorry?
Decidability?
Yes, so I mean, you can have Tableaux for full first order logic, and of course that is not decidable. Yeah, but generally speaking, the idea is that the way to show decidability with Tableaux is linked to its analyticity, right? So the idea that if you keep chopping, so the problem with first order logic is that you might enter loops and things of this sort. But the decidability usually comes as a consequence of the chopping of Tableaux. Yeah. Because actually you can define, so think for example about you know that Peirce's arrow is expressively complete. So you could think, okay, this is a very nice example. Let's define Tableaux making use only of Peirce's arrow. And the problem that you have with this is that you might have a formula involving Peirce's arrow, and the corresponding tree rule gives you a longer formula, right? So the idea is that in that case, although let's say conceptually the rule is well motivated, the problem is that that rule is not working to smaller pieces. Okay, so now one nice way to look at strong cleaning logics is looking at the shape of their counterexample. Okay, so we have two logics. Well, all these logics is super well known by all of you, of course. And the K3 and LP are the more traditional logics that you can define on these strong cleaning semantics. The idea of K3 is that it preserves value 1, and the idea of LP is that it preserves value non-zero, right? You can reformulate the definition of logical consequence in terms of the shape of their counterexample. So a counterexample in K3 is an interpretation that makes all premises 1, so all premises take value in this set, and all the conclusions take value in this set. Okay. A counterexample in LP is an interpretation that assigns all premises values in this set and all conclusions values in that set. Okay. Now you can also define ST and TS. So the idea is that in the case of ST, an argument is valid when there is no interpretation making all premises 1 and all conclusions 0. So if you look at the shape of counterexamples in ST, a counterexample should assign to all formulas a value here and to all conclusions a value here. While in the case of ST, a counterexample must assign to all premises a value in this upset and all conclusions a value in this downset. And of course, you notice that there is a characteristic shared by K3 and LP that is not shared by ST and TS, which is that in the case of K3, the shape of their counterexamples are exclusive, and so the upset and the downset for the counterexample are exclusive and exhaustive. While in the case of ST is not exhaustive, in the case of TS is not exclusive, right? So the non-exclusivity of the shape of the counterexample is going to give you an immediate failure of reflexivity, right? Because you can have A implies A. Well, if you give it the value that is in the overlap, that will give you a counterexample to reflexivity. And something similar, not exactly the same, but something similar happens with the case of ST. So the fact that the upset and the downset for the counterexample are not exhaustive will give you a failure of transitivity. Now, a failure of transitivity in a local sense, not necessarily in a global sense, okay? Okay, so again, well, we'll write that an interpretation makes a formula strictly true. We will usually write it this way. And strict truth and tolerant truth are duals in the sense that A is strictly true in an interpretation just in case the negation is not tolerantly true, okay? And this duality is going to play a role in our trees. In order to simplify our trees, we don't need to use a tag for strict truth and a tag for not a strict truth. So instead of saying this is not strictly true, we will say the negation is not tolerated, okay? So that our trees only need two tags, strict and tolerant, okay? You will see it here. So an argument is XY valid, where X and Y can be S or T, exactly when, so the initial list will list all the premises with the index X. So suppose that we are talking about K3, so this is SS. The initial list will be the premises with S. And instead of writing the conclusions with not Y, what we write is the negation of the conclusions with the dual tag, right? So if Y is S, the dual tag is T, okay? And I think it's a good trick to not to multiply tags without necessity, okay? So the initial list for K3, write tag S for the premises and tag T with a negation, of course. On the conclusions, for LP, tag T and tag S with negations in the conclusions. For ST, you have tags S, and for TS, you have tags T. Now, a very nice feature of the strong Cleany schema is that the tree rules are the classical tree rules. So actually, the trees, the strong Cleany trees are going to be identical to the classical trees except for the tag. And the only thing that we have to do is to keep the tag while you are applying the rule. So if you have here S, then this will be S and that will be S. And the same for this non-branching rule. So if here you have T, then these two should keep the tag, okay? Now, closing condition, yes?
Very nice. Whether it could be generalized. You're focusing on strong Cleany because sociological, historical fact, but this trick could work also for any logic with a negation of kind of negation of something, right? Not the three rules, but the definition of negation. Because it depends on fitting the one part or not.
You mean with three truth values?
Yes. Maybe I'm wrong. Maybe we could think about this later, but
no, in principle, so the trick will work because this let me see. So for example, in the case with Cleany, I'm not completely sure. I'm not completely sure. Yeah.
But even in the strong cleaning case, you want to be able to express, for instance, a logic that goes from strict to non-tolerant. In that case, the negation won't work. So it's like if you consider all the possible standards from the strong cleaning algebra, you will need more than one that negation. So that it won't work. More or less for the same reason that if you extend the
But you are not making any standards. You are only considering the absence for standards.
no, so I understand that was the question. If
No, I think the question was if this is just peculiar of the strong cleaning, this trick of taking the negation of the conclusions and the one of the standard of the conclusion, or it could be used for other schemas when the negation of 1/2 is 1/2 and negation of 1 is 0 and the
I think the answer is no. And actually, I should know this because I read a paper. But I wrote that paper.
But I'm going to check and give you an answer. But I think the answer is no. So if you have different negations, so it must be a strong cleaning negation. So in the case of weak cleaning, the negation is the same. But if you have a different negation, that won't work. So you need that negation that flips 1 to 0 and the middle value to itself. I think it does work, but I need to so I'm only like 70% sure. Okay, so thank you. Closing conditions.
Sorry,
Yes.
before we wrap up, also the complement to this discussion to be something complementary, right? Keep the rules, same rules as in classical logic, but maybe the way you set the list for certain logic has to change. You keep it even if it's tree value, even if it's the definition of logical consequence, maybe it's ST or LP. You keep the rules because maybe the truth tables they allow, but how you set the initial list maybe has to change.
Yeah, I'm not sure that this can be on a
Generality, because in the case of weak cleaning, I don't think at some point I thought I could. So I don't think that you can make use of rules with only 2 branches. So in the case of weak cleaning,
No. You can also have a tree-value logic with a complementary situation where you can keep the rules, but they need to be a little bit different for completeness and so on.
Yeah. So I don't know. I believe that in the case of weak cleaning, you cannot keep the classical rule.
You cannot.
You cannot. Okay, so closing conditions. So here the idea is also very simple. When you have a formula and its negation, this will close except when both tags get. So
there you have S and T. So basically, you're saying here A takes value 1 and negation A takes value non-zero. Well, that's impossible, etc. When you have a formula with T and its negation with T, well, that's exactly the case where the interpretation should assign to this formula the middle value, and this is something allowed by the semantics. Okay, so let's look at a couple of examples. So we have here the tree for K3. So we start with premises and the strict sign or strict tag, and the negation of the conclusion and the T tag. So we develop this from the negation of the conclusion. So we just keep the tag, then we apply the rule to the first premise. We have here negation A with S. We have here A with T. Well, that's enough to close the branch. Now we unfold the second premise, and we here have negation BS and BS, and this will close this branch, and negation, sorry, CS and negation CS, sorry, negation CT here, but that will close this branch. So this shows that the conditional is transitive in K3. Now, what happens in the case of LP? Basically, you can transform any K3 tree into an LP tree just by swapping the tags, right? And if you remember, we had here a branch closed with BS and negation BS. And so this branch here, negation will have negation BT and BT. So this branch will be open. And again, the open branch will tell you how to construct the counterexample. Since we have BT and negation BT, then B must have a value half. We have negation CS, so C must have value 0. And here we have A is strict, so A should take value 1. Now, the case of ST is super simple, because since ST involves only S tags, a classical tree will close exactly if it closes in the case of ST. So if a classical tree closes in the case of ST, that tree will close with S and S. So since we have only S, oh, sorry, I forgot here the S. Since we have only S, there is no possibility that that you have an open branch with AT and negation AT, okay? So this is an easy way to see that actually ST is inferentially classical logic, or the valid inferences of ST are exactly the valid inferences of classical logic. And in the case of TS, it is also easy to see why TS is empty, because we have only T tags, so any branch of any tree in TS is going to be open. Now let's move to meta-inferences and a little bit of motivation. So why are meta-inferences interesting? Well, in classical logic, you have that an inference is classically valid just in case the conjunction of the premises, conditional conjunction of the conclusion, sorry, disjunction, this is a typo, disjunction of the conclusions is valid. So in a sense, in classical logic, you don't need to ask yourself about the validity of an inference. If you have a theory about tautologies, this will give you a theory about the valid inferences in classical logic. But we know that this is not, this doesn't hold for all logic. So for example, oops, I didn't write it here. In the case of LP, we have that LP, the valid tautologies of LP are the valid tautologies of classical logic, but not all valid inferences in LP are, sorry, the other way. So some classically valid inferences are not valid in LP. So the idea is that in the case of LP, if you look only at the valid formulas, then you will lose something about the nature of this logic. And exactly as Eduardo and Diego and Lucas showed some years ago, so like 10 years ago. So exactly the same situation happens with the meta-inferences of ST and the valid inferences of classical logic. So that if you, in the case of ST, if you look only at valid inferences, then you won't get the full story about this logic. So you need to look at meta-inferences. Okay, so you can define a meta-inference. You have the usual definition of a formula. Then an inference is an arrow with formulas on one side and formulas on the other. A meta-inference is a special arrow with inferences on one side and inferences on the other. We will stick to a formula and inference formulation. So actually defining this for multiple premises of inferences and multiple premises of conclusions is not difficult, but it's very cumbersome. So I'm gonna make the easy thing here. So we can define satisfaction for an inference. An inference AROB is XY satisfied by an interpretation when either the premise, the formula in the premise is not X satisfied, or the formula in the conclusion is Y satisfied. Now we can extend this notion of satisfaction for an inference to satisfaction for a meta-inference. And well, this is the way of defining the local notion of meta-inference validity. So we will say that a meta-inference is XY satisfied when either the inference in the premise is not XY satisfied, or the inference in the conclusion, sorry, here there's a missing X, or the inference in the conclusion is XY satisfied. And we will say that a meta-inference is valid when is XY valid when is XY satisfied by every interpretation. Okay. Super. Okay, how to tune our trees in order to deal with meta-inferences? Well, the easy trick is you have to add inference arrows to your tree. So in the same way, the tree for an inference departs from an initial list with formulas. The tree for a meta-inference, I think someone's asking something, or
yes, a minute ago.
So it's not a question for me?
I think so. Where is the type? Where is the type?
The typo for
At this, this one. So here it should say XY. And here, instead of conjunctions, it should say disjunctions. So I wrote this conjunctions here, but it should read disjunction. Ok. Necesito que le hagas algo para que vaya. Ahí. Thank you. Okay, so in order to write our tree, so the idea was, in the case of inferences, the initial list have formulas. Well, in the case of meta-inferences, the initial list will have inferences, right? And so we extend, if we want to check whether this meta-inference is valid, we will write the inference in the premise, which must be XY satisfied, and the inference of the conclusion must not be XY satisfied, okay? So basically, this initial list is telling you we have an interpretation which is a counterexample to this meta-inference. And now we expand our tree rules to cover the case of inferences. So in the case of AROB is not XY satisfied, well, this means exactly that A is X satisfied by the evaluation and B is not Y satisfied by the evaluation. But remember that B is not Y satisfied is the same as the negation of B is dually satisfied. So in a sense, these rules are very, very easy to for me to remember, because it's just the rule for the conditional, but you keep the tag for the unnegated and you change the tag for the negated, okay? And the same goes for the second rule. So A arrow B is XY satisfied when either A is not X satisfied, but then we write negation A is dual X satisfied, and B is Y satisfied. So again, easy to remember. So it's the rule for the conditional. In the unnegated case, we keep the tag. In the negated case, we write the dual of the first tag. See? One example. So suppose we want to check whether oh, this is K3, I don't know why. Yes. Yep. Alejandro.
If you have to implement no, you are mute.
Alejandro?
Okay. Thank you. Can you hear me?
Yes.
Yes.
Okay. I have only a very tiny question. When you define meta-inference satisfaction, you define it like a classical conditional, right? When either you don't, you can satisfy the antecedent, or you can satisfy the consequence. So it's like a classical conditional in the meta-inference satisfaction. It's right.
Yes.
Okay, and there is a special claim or an special motivation for that, for define satisfaction in the classical conditional, or in the classical set of conditional?
Super good question. Thank you very much. But actually, I'm not gonna answer right now because I will talk about this in the last bit of the course. But I can tell you this. So you have like the local notion, which is this one. So basically, it tells you that a meta-inference is valid when there is no interpretation, the same interpretation, that is satisfying the premise and not satisfying the conclusion. Okay, this is the local one, and you define it in this with this material condition. Reasons for this: elegance. So this will give you a super natural and nice way of developing trees. Or if you want to write it in terms of sequence, it will give you a very nice proof here. There is a second notion, which is the global. The global tells you that a meta-inference is valid when either the premise of inference is invalid or the conclusion inference is valid. Okay? The global notion is, in some senses, I think it's more natural than the local. It will give you a very messy proof theory. You can do it. Okay? In general, it will give you a messy proof theory. The way I understand validity for meta-inferences, the way I think is the right way, there's something like this, to understand validity for meta-inferences, is the global, but not with a material condition, but something like a strict condition. But you will have to wait. I'm sorry. This is what I can say for now. And if you're happy with it or.
Okay, thank you so much.
But good observation, yeah. So actually, the idea of Alejandro, if I'm not wrong, is that you, oops, yeah. No funciona. Ahora. So the idea is that
here you can have something different, just material. Actually, this will give you room for defining different notions of meta-inference stability. Okay, so here the example, it should be here K3. So this is like a meta explosion, we said. So the meta inference is telling you that if A implies contradiction, then A implies C. So this is valid in the case of K3. We write the premise with SS. We write the conclusion with SS negated, and then we unfold first this the conclusion. So we have A with S and C with negation C with the dual tag, right? So instead of S, if you think about it, actually this is the initial list when we try to prove that something is K3 value for inferences. No coincidence. An inference is a meta-inference without premises. At least, I think Eduardo might have an opinion, but. Okay, then we apply the rule here. Remember that, yes.
You use just the dual.
Yes, yes. So basically, so here you have SS, right? You develop as a bit word additional, but here you are the negation, and instead of this S,
You are applying a function, but you're just
you automatically transfer this to T, right? And so, yeah, the way I see it is, this is a compact way of writing the four rules where you have SS, ST, TT, TS. And in this second case, we have here yes, and this is going to transform into negation A with a T. We have already S here, so this one closes. And here we have B conjunction negation BS, and of course this one is close. Okay. And of course, we can see that in the LP3, this is going to be open. And the counterexample tells you that C must have value 0 because you have negation C strict. So C must have value 0. B must have value 1/2. And A here, it tells you only that A must be tolerated. So A must be non-zero. Okay. Now what happens with ST? In the case of ST, we have a tree is open, but the induced counterexample must assign to A the value 1. So there is a small difference here between LP and ST. The assignment where A takes value, the middle value is not enough to produce a counterexample to meta explosion in ST. And in the case of TS, so TS used to be empty with a lot of inferences, but it turns out that this meta inference is valid in TS. Okay, very quickly, this is something with Joaquin and Martina, Xavi, and Isabel. We explored how to extend this kind of tableaux or something very similar to the case of the Belknap-Bloom semantics.
Before going to that in the review, you are given the example of single inferences each time. What about if you don't have a premise? How would you start the tree?
If you don't have a premise, like
let's say XY dot return arrow the arrow B. Something like this.
Okay, so instead of the empty set, you will put the top.
This thing, of course, holds for any selection of tags. So it's like it's not in the tree, it's not gonna play the role in the tree. And then you write A arrow B, XY hat. This will give you the initial list. The initial list to check whether this is XY value. See?
And when you have the empty sequence as a premise, you also use this top and bottom thing, right? For instance, as a premise of a meta inference, you have the empty sequence.
Yeah.
So that would be meta inferentially valid no matter the conclusion, because the premise cannot be satisfied because it's the empty sequence. So
I'm not sure I'm getting your point, sorry.
when you have like
The empty sequence, you mean like something like this?
well, you can translate that in that way. Yes. Like empty set, right arrow empty set. You can translate that in using a button that would do the job. Because we are also developing these tableaux and we have a special condition, closing condition for this.
Okay, okay. But I understand that the empty sequence is something like it's like this, right? So it will always close.
Yes.
Yeah, I agree. The nice thing of using this is that in the end it will be equivalent, but negating this looks very ugly. Negating this looks like it's natural. Okay, so one interesting thing about the Bernard-Lu thing is that, of course, you can define FD, you can define exactly true logic, but again, here we have
the shape of the counterexamples are exhaustive and exclusive. But you can go to something like the for-valid analog of ST, which will be something like this. All the premises take value here, and all the conclusions take value here. Interestingly enough, it is not, it doesn't, in the case of 4 truth values, it doesn't coincide with classical logic. And you can also have like non-transitive and non-reflexive logics. So logics where the upset and the downset of the counterexample both overlap and don't exhaust, right? And I think I finished with the first part. I can continue with the. How much time do we have?
1 hour and a half, no, what the original plan.
As you wish. So I think probably the third talk is much longer than the previous ones, and probably it will generate more discussion. So if we can advance, so if we can finish sooner with the first 2 talks, which are much more standard, it will give us more space. But as you wish. Sí, continuamos. So some of them have a name, and some of them we just call them by their tags. So the thing, yeah. So these ones here are this graph shows the counterexample inclusion of these logics. The yellow ones are non-reflexive, so they are empty. So for many, they are inferentially empty. So for many, they are like worthless because they are empty, but they are not empty at the level of meta-inferences. These ones are the non-reflexive and non-transitive. Now, since they are not reflexive, what happens is that they are empty at the level of inferences. If you take a global notion of meta-inference validity, then they are transitive. They are transitive, so they are non-transitive only in the local sense. But if they are, I mean, if a logic is empty, then the meta-inference corresponding to transitivity is automatically valid because the premise inferences are invalid. Okay, and yeah, this one is FDE. So this FDE is equivalent to this logic, but it's not equivalent valuation by valuation, which is also interesting. So the idea is that if an argument has a counterexample here, this argument has a counterexample here, but it need not be the same counterexample. But you will say that this logic, I mean, the natural stance is saying that these two are the same logic, and this one and that one also are the same logic. Yeah.
Well, we'll start the second part of the course. Thank you, Pablo.
Okay, so I'm afraid that this is what we are going to talk about now.
It's very standard stuff, so probably you know it by heart. But just in case, I prepared these slides for the third part of the course, in case we finish with this very, very quickly. Okay, so the second part of the second part of the book is about modal semantics, and well, a little bit of motivation about the origins of modal semantics. As you know, modal logic is at least as old as Aristotle, but the modern origins of modal logics has its roots in C.I. Lewis' paper of 1912, which was implication on the algebra of logic, in which Lewis discusses the conditional of Principia Mathematica, and basically what Lewis says that this is not the conditional we use in English, and he proposes a new conditional called strict implication. He doesn't call it conditional, but implication, and that's why Quine later on said that modal logic was fue concebida en pecado. I don't know what's the expression in English. And well, the idea is that actually the Lewis, yep.
in order to connect inference. No?
Sorry.
When you use in the last presentation, you use in order to produce meta inference in the language, you use a double arrow or triple arrow, I don't remember. But the movement is relatively similar. I have crazy ideas.
No. I mean, I see that there might be some connection, but this, I think, the script implication has a modal component. That's not, at least not present.
But it's the idea to have an environment in the language.
Okay.
In this way.
Yeah, like pushing
Exactly.
to the object language.
The modal component is not the same.
Thank you. So actually, the set implication of Lewis's can be understood as a box conditional, and well, probably you know that initially modal logic developed in an axiomatic Hilbert style pattern, and this didn't help much for the philosophers to really have an interest on the area because it was super messy. Like you have all these axiom systems, etc., and just substitution and model fullness to write groups, something well messy, hard to do, something happening. And model logic consolidated the area of intensive research after creating these two papers in the late 50s, in the beginning of the 60s. Okay, so the people usually say that classical logic is extensional in the sense that the truth value of a sentence, in a given interpretation, depends entirely on the truth value of its component expressions. Or more generally, the truth value of a sentence depends on the extensions of the expressions involved. So about the objects that are the reference of similar terms, sets of objects that are the extension of predicates. And a hallmark of extensionality is the rule of substitutivity of singular terms with same reference, which tells you that if some property is true of an object T, and it turns out that T and U have the same reference, then that property holds of U. And so, for example, in classical, well, this is actually a rule of classical crossover logic with identity. And a typical example of a substitution is the following. Giorgione was an Italian painter. This is true. It turns out that Giorgione is Barbarelli, so we can substitute here Giorgione by Barbarelli. And the truth value of the sentence remains positive. So Barbarelli was an Italian painter. But there are contexts in which this rule no longer works. And these are so-called intentional contexts. Usually, I think the very rough idea is that some expressions generate like a context where the expressions that appear after this first expression are like, well, I'm contributing here not just with the extension, with something else, intentional. So some life examples, Giorgione was so called because of his size. It seems that his name was Giorgio, but he was like Orsato, so a very big guy, so Giorgione. Giorgione was so called because of his size. Giorgione is Barbarelli, but it is not true that Barbarelli was so called because of his size. Barbarelli was called Barbarelli because it was his father name or something like this. So what happens here is that in this context, the so-called takes as a reference, not the reference of this expression, but the expression itself. So there is like in this sentence here, there is a double rule that the expression Giorgione is playing is simultaneously used and named. Lois Lane believes that Superman is brave. Of course, Superman is Clark Kent.
So Lloyd Lane believes that flat plane is right. This is false. Well, I will say that this is false. I think we didn't right. It's not working. It's not. Yeah. So I will say this is clearly false. It is false means the dictum attribution, right? So if the way we make reference to Superman is involved in the belief attribution we make in the first account. There is an X such that X is Superman, and Lloyd believes that X is brave. That will be the right reading, or the dictatorial reading will be Lloyd Lane believes that there is an X such that X is Superman. And something similar with modal expressions. Necessarily, 8 is bigger than 7. 8 is the number of planets. It used to be 9 actually, and I think in the classical examples is 9. And well, these two things are true, but necessarily the number of planets is more than 7. Well, there might have been like a quantum jump in the original conditions before the Big Bang that made our universe our solar system had 6 planets instead of 8. So this one is false. Well, it's false in its the dictum reading. Okay, let's go for the modal trees. For the semantics, the language, it is very easy. We have just to expand our language. So we have the conjunction, disjunction, the negation, and we add 2 expressions, the box and the diamond, which will be our modal expressions. And an interpretation is going to be a triple, while W is a non-empty set, R is a relation in W, and the interpretation there is a typo here. So the interpretation function goes from variables times possible worlds to truth values. So the interpretation assigns to each variable and possible world a truth value. Or if you want a truth value to each proposition in its possible world. The truth conditions for conjunction, disjunction, and the conditional and negation are the same as the classical, but this time things are relative to positives. So A conditional B holds in an interpretation in a possible world. If in that possible world either the antecedent is false, conjunction takes value 1 in W, exactly when A takes value 1 in W and B takes value 1 in W. The words play a substantial role in the definition of the modal expressions. So we have that the box A takes value 1 in W when A is true in all accessible worlds. So for every X is accessible from W, it should be X here. So for every X, if W has access to X, then the value of A in X is, and diamond A takes value 1 in W when there is an X to which W has access, and in that X, not W, in that X, A takes value 1. Okay, so notice that in dead ends, so the ones that has no access to any world whatsoever, boxes take value 1 and diamonds take value 0. Okay.
Now, logical consequence. So there are different ways in which we might want to find logical consequence. But for many readings of the box and diamond, such as the object extending or modal meanings, the natural way is understanding that the informal notion of truth corresponds to truth in a world. Okay? So logical consequence should preserve this property, truth in the world. We will say that an argument with premises A1 to AN and conclusions P1 to BM is valid just in case there is no modal interpretation with a wording such that all premises take value 1 in W and all conclusions take value 0 in W. Okay, so let's go for trees. Now the modification for trees this time, we'll have two kinds of nodes. We have formulas with a natural number, or we have natural number R natural number. So the first one is talking about a formula being satisfied in a number. The second one about the access that a world has to another. Yeah. Alejandro.
Yes, in the previous slide, or two previous slides, when you define what is truth in, how is truth the necessity of A and possible A, the another one. Previous of that. In the down part, when you say necessity of A, it's true in a word W when for all X that W have an access to that X. I see that there is an error. No, it's B, it's BX. It
should be an X here and an X here as well.
Yeah, I don't know if that was an error or only a confusion for my part.
It's a typo. Thank you very much.
Okay, thank you. So, sorry.
No, it's fine. Okay, so we have new nodes. The first kind of nodes talk about a formula being satisfied in the world. The second one about the access that worlds have. So our initial list will depart from a list of formulas followed with number 0 and the list of the negation of the conclusions with number 3, right? And here the idea is that in order to produce a counterexample in the local case, we need a world, and in that same world, all the premises are true and the conclusion false. Now for the three rules, the rules for the connectives are the same, but you have just to pick a number. So a conditional is gonna be satisfied in a world J when either A is false to J or B is true. We have a couple of rules that embed the negation. So the idea is that we want to keep topping things, right? If you have a box with a negation in front of it or a negation in the diamond, what we do is we push the negation inside and change the box by a diamond and the diamond by a box. And the really interesting rules are the proper modal rules, are the diamond and box rules. And there is a kind of asymmetry here. So if you have a diamond in a world J, then you have to introduce two pieces of information. The first one tells you that J has access to N, where N is a new number not in the branch. And then you write that A is true in N. So here the idea is the same. Probably, well, you know this by heart, but the idea is that
when you're looking for counterexamples, the diamond is telling you that there is some world where what comes later is true, and we want our procedure, our search for a counterexample not lose generality. Okay, so in order not to lose generality, you need to introduce a new word, which can be any word whatsoever. If you use a word that it was already in the branch, then that word is not any word, so to speak. And in the case of the box rule, so box A holds J, if we have only this information here, we cannot apply the rule for box, so we need further information. We need box A and J, and the information that J has access to. When we have these two pieces of information, then we can apply the rule for box, and actually we have to do it as many times as nodes from J are we encounter in the. Here's a little example. So we have this premise, the negation of the conclusion. We unfold this negated disjunction into this. We transform the diamonds into boxes. And now, at this point, we cannot apply the rule to the boxes. We have to wait to find some accessibility relations. So we apply the rule to the first premise, which unfolds these two pieces of information. So 0 has access to 1 because 1 was not in the branch, and A is actually 0. And once we introduce this accessibility here, then the boxes, we have to apply the rule to the boxes. Okay, I applied first a rule for the disjunction, opening this branch. Then this box goes here, and this box goes there, right? Producing the closing of the branches. Okay, of course, when a tree is complete but open, the open branch will give us the material to produce the counterexample. So take the example of this argument. This argument is not valid so far. So P conditional Q in 0, box Q conditional R in 0, and we negate the conclusion. The negation of the conclusion unfolds this way, and then we apply the rule to the first premise. And what happens here is that since we don't have any information that 0 has access to some world, we cannot apply the rule to the box, right? Basically, this corresponds to what we were saying about boxes are automatically true in their ends.
Yes. Right. How do we get to step where we have the relation through the diamond rule?
Sorry?
How can we get to a step where we have the information of the relationship between two words through the diamond rule? Okay.
Or else, as we will see, in some cases, so we are now like explaining the rules for the most basic model system. So for example, in KT, you can introduce information about the accessibility relation. Okay.
Which form? I'll wait, but in which form? Like as premises or
you introduce it as basically as new rules to the
okay.
Similar to Chris' book. Remember,
similar. This is exactly what Chris does in the book.
You could add that step to prove the connection between words and the restrictions is similar. In this concern, not in the other. It's different.
So, okay, this is a very cheap example. In the case of in the case of K or the system that we are explaining right now, we have to wait until we have some information about the assembly relation. So the counterexample produced here is very disappointing because it's we include a possible world by each number. So we have only 0, so we have only one possible world. And then the interpretation tells us, that Q must be true here, that R should be false, and that P should be true. And here the part of the idea of the counterexample is that W0 is a dead end, so that this box here, even though we have a Q and location R, so that Q conditional R is false, this box here is valid.
Pablo?
Yes.
In the case of the counter models that require that one has access to itself, that will happen also in the tree.
So if you require that the model, the world has so it reflects the interpretations, this is going to be valid, of course.
No, but the reason is when you have a particular common example that makes the connection in one point, the derivation will tell you that explicitly. So you will have a step that says 0.
Yeah, yes, right. Exactly. Okay, so the idea is that in many readings of the books, so if we read it in an epistemic, let's say, or in a modal, probably modal reading of the books, we would like that the inference of both being. So we would like to have a system that is stronger than the system we present. From an axiomatic point of view, the way of strengthening
a system is by you have a list of actions, and then you add to this list of actions some formula that is independent of the actions, so that this guarantees that you will strengthen the resulting system is going to be stronger. And from a semantic perspective, in order to get extensions of the original system, what we do is introducing restrictions on the interpretations, which at least to my students, this looks a bit strange, right? Like less interpretations, more valid arguments, but of course it makes sense because if you define logical consequences absence of counterexamples, the less interpretations you have, the less chances you have to find a counterexample to the argument, right? So basically, yep.
So they're going to get NEC for free, but I don't remember if in your book you consider the non-normal system of Bohan.
I don't.
So the previous one has the satisfaction of the necessitation rule.
Yes.
Yeah, exactly. Yeah. But it is possible to have Tableaux for non-normal.
Yes, so basically, if I remember correctly, you need to introduce non-normal words, basically in your Tableaux, so that I think it's each time you open a new world, the new world must be numbered. Where diamonds 4, by 3, right? And boxes are 4s. Okay, so these are the name of the axons and the interpretations in connection to which each of these axons has no counters.
Sorry, the K axon.
Yes. This is the type of. So these 2 boxes should be out. Thank you. Well, probably you are very familiar with this. Okay. And in order to capture the strength of these actions, what we're going to do is add specific rules in order to mimic the property of the accessibility relation that you are concerned with, right? So for example, if you want to prove that something is valid in KD, so the result of adding this action to system K, which means in terms of interpretations, serial, you are focusing on serial interpretations, you add a rule that allows you to extend any tree with E and N, where E is any number that is already in the branch, and N is minimal. So this mimics this condition expressed in a first order language for all X there is a Y, such that X has access to Y. The same goes for a perplexity. So if we add the action T to K, we get a system KT, which is sound and complete with respect to reflective interpretations. So in our trees, what we are going to do is adding this rule that allows us to introduce the information that any word in the tree has access to its well, just notice that in order to prove completeness, the addition of these rules, what they are going to do is basically when you have a complete open tree, the induced counter model will have the expected properties. Right? So if you make systematic use of the rule of reflexivity and you have a complete open tree, then any branch of the tree will induce a reflexive interpretation. So basically that's the observation. So for example, in our example above, in the case of K, the tree ends here. In the case of KT, we can apply a new rule, which is the rule corresponding to reflexivity. I don't know if this was your question, Liliana.
No. It was just how did you get to that information, and was through the rule in the first system.
Okay.
Through the rule of the diamond, that was it.
So I didn't address your question.
No, yes.
Okay.
Thank you very much. It was a very simple.
So basically, here, so we have a new rule. We can extend the tree with this information, and this triggers the application of the box rule here, right? So from box preconditional C in 0, and the fact that 0 has access to itself, we need to write this new line and then this blocks the tree. I don't know if you know the tree proof generator. It's a very, very nice tool. So I was too lazy to write all this. I'm gonna ask you
to this prover. It's quite nice actually. So this shows it was in KT4. This argument is valid over reflexive and transitive interpretations, but it's not valid either in KTB or KT or KD. Okay, and we go with we are almost done with this part. Let's have a look to two very related systems, which are KT5 and KU. We'll say that a relation is Euclidean exactly when, if a world has access, a world 0 has access to W1 and 0 has access to W2, then 1 has access to 2. So this, as you can see, this condition is a kind of mix between transitivity and symmetry. And the formula Damon A box Damon A is valid in Euclidean interpretations, but it is neither KTB nor KT4 valid. And when we add this formula to KT, we get to the system KT5, which is an extension of both KTB and KT4. Now, why? Well, the semantic way to see why KT5 is an extension of KTB and KT4 is based on the fact that if a relation is reflexive and Euclidean, then it is symmetric. So if a relation is reflexive and Euclidean, then it's symmetric. So suppose that X has access to Y. So we need to show that Y has access to X based on reflexivity and Euclidicity. I don't know if this word makes sense. So since R is reflexive, X has access to X, and then by Euclidicity, Y has access to X, right? So this nice graph here shows that reflexive and Euclidean relations are also symmetric. And the second fact is that if a relation is Euclidean and symmetric, then it is transitive. And so suppose that X has access to Y and Y has access to Z. Now we have to show that X has access to Z, but we showed already that reflexive and Euclidean relations are symmetric, so we can use this fact. So Y has access to X by symmetry, and by Euclidicity, again, X has access to Z, right? So here the idea is that reflexive and Euclidean relations are equivalence relations, okay? Yep. Yep. Mm-hmm.
The other direction, right?
Since it's a universally quantified statement, it doesn't matter. So it has a single string.
So you mean that it doesn't change the, but you may make it double.
So in terms of a first order language condition, what you're saying, if I'm not wrong, will be then Y has access to Z and Z has access to Y, right? But these, since here Z and Y are any elements, but you are not really having any string text. Okay?
Yeah, I think in some textbooks it appears only. I mean, mostly it appears the way you are saying. Sometimes it appears like both ways, but really doesn't make a difference.
Well, it does that you have to write more things. But I think that is more elegant if you go for the shorter formulation. Okay, but it's equivalent. Okay, so an argument is 85 valid, just in case there are no reflexive and Euclidean counterexamples, which is equivalent to there are no counterexamples with accessibility and equivalence relation. we'll say that an argument is KU valid just in case there are no counterexamples where the accessibility relation is universal, so that R is W times W. Now, since any universal relation is an equivalence relation, this gives you automatically that KU is an extension of KU. Here the idea is that we apply this sort of reasoning over time. Since the interpretations for KU, so any universal relation is an equivalence relation, and so the interpretations for KU are a subset of the interpretations of KT. This guarantees automatically that if an argument is invalid in KU, so if there is a counterexample to an argument here, then of course this automatically gives you a counterexample in KT5. Or contrapositively, if an argument is valid in KT5, then it is valid in KU. And now, since at least this is what my students expect in Pamplona, so each time we shrink the set of interpretations, we get proper extensions. You will expect that since the universal relations are a proper subset of the equivalence relations, you will expect that KU is stronger, right? So, but there are arguments valid in KU that are not valid in KT5. Of course, all of you know that this is not the case, and it's a peculiar result of the normal modal logics that any KU valid argument is also a KT5 valid. Okay, and the idea of the proof is very easy. So suppose contrapositively that an argument is not KT5 valid, then there is an interpretation where the accessibility relation is an equivalence relation, and a world where the premises, call it W0, the premises are true and the conclusion is false. Now, this interpretation will not be an interpretation where the accessibility relation is universal, right? But the trick here is that an equivalence relation divides the space of possible worlds into equivalence classes, which are sets where any member of the set can see any other member of the set, but no member of the set is related to a member outside of the set. So the idea is, well, define the interpretation, which is the restriction of W to the equivalence class where W0 is, and then just prove all the worlds outside the equivalence class, and then you get an interpretation which is a counterexample in KU for the argument. Right? So in this new interpretation, the relation is universal. I cited myself. Just in case. Okay, we're going to talk about two more extensions of K, which are the trivial system. Okay, the trivial system is the result of adding this axiom to KD at least. So it is not enough to add it to K. And the verum system is the result of adding box A as an axiom to K. So now the question is, can you figure out how to adapt our trees to these systems? How to how to adapt the trees. That's the question. So do you wanna add some rule or
Remove all the modern rules and move to classical.
it's end of collapse in the classical logic? I suppose in the case of Verum, you have to add closing conditions. Right? So you have your closing conditions are A and negation AM. Each time you have a box, then you close comments. And you have to modify also the rule for the diamond until you cannot develop further any line. So the idea is that you are treating this as bottom and the other way, sorry, the other way. So diamonds close a branch, and boxes cannot be extended. Well, of course, if you don't need to say anything about the box if you are working with trees 4K, because trees 4K only generate accessibility relations via diamond. Okay, so you have to add only this closing condition. Then you are done. Instead of changing the closing conditions, can you show the right for the formula and station? So instead of adding a closing condition, can you just add a rule that from the diamond A you can write the formula and its negation? That will be another option. So change your tree rule for diamond to this one. Okay. In the case of trivial, what would be the
Semantic condition for tree is that every word sees itself and only itself.
there is just one word?
Yes, well, it's equivalent to say that there is a
No, okay. I get it. Only itself, you're right. And well, it will be introduce this rule that from a formula you can introduce from a formula you can introduce box A. Actually, we are going to see this rule box introduction later on in the case of supervaluationism. And the addition of this rule to KD is enough to trivialize all modalities in the sense that box A becomes equivalent to A. And you can see that with KD plus this box intro rule, you can prove you can prove the action for KT, right? So you negate the action, you have box A, negation A, then you introduce the box. Since we are working in KD, 0 must have access to 1, and then you get the contradiction.
It's like a truth.
Yeah, so that's an interesting way of looking at it, because in the case of supervaluationism, the box is some form of talking about super truth. Okay, so actually you can see that the supervaluationist will want to avoid this equivalence, right?
One thing that unfortunately, I remember perfectly the way you presented the project, but if I remember, you presented those systems based on rules for the accessibility relation.
Yep.
Here you're giving a rule for the model, right?
Yep.
But you're keeping this, or you're, well, it seems that it is actually, I mean, of course it's fine. I mean, I'm not saying it's fine, but it's very different because previously you said that model systems are generated by inspections on the accessibility relation, and now you are saying that it's equivalent, but that is generated by a new rule. And
yeah, okay. So you can do it from the more semantic point of view, saying, I suppose, something like like a rule telling you something like this.
there's only one.
Yep. No?
I don't know.
The box intro plus, changing the closing condition to box A, and that's it. That makes sense.
So I can
Okay, so for trip, in order to get it, add the box intro rule plus that box A closes. That makes sense.
I don't think so.
Okay.
Because the effect of the trivial system is that modalities play no role whatsoever, right? So the idea is that you have a formula where you need to have some boxes and diamonds inside. And in the case of trivial, this formula becomes equivalent to the formula without utility. But you can have, let's say, box P, this is satisfiable. The rule will make it
Exactly. Yeah. Thinking of triviality like in the whole sense. Okay, thank you.
It's trivial for the modality.
Right.
So actually this so these two are presented in the classic book of well, as ways of collapsing into classes. Do we have time for something else?
Yes, sure.
Yes.
I remember. 1 hour.
Okay, so so in this last well, today and tomorrow, because the thing is that I realized that I have a lot of slides about these two topics, so I think it is better to try to cover some things today, and we'll have something more to discuss. So the idea is exploring two different topics. One is about the supervaluation steering payments, and the second is about how to understand, or at least the way I think we should think about validity.
We go supervaluationism. So usually when discussing vagueness, people focus on two different topics. One is borderline cases, the other one is the Schleicher's paradox. And the idea of borderline cases is that there are cases that could fall under a predicate, and that apparently we have the right expertise about the language, the information about the case in question, but somehow we cannot decide whether this object falls in the extension of the predicate. So, well, I don't know if Williamson is free, but this is the example he thinks that we use in his book. So the idea is that when you are asked whether Williamson is thin, you won't say, all the people say yes, he's thin, or no, it's not. If he's a borderline case, there will be a sort of symmetry in these positions, so that they will give some qualified answer, like sort of, in a sense, he is, in a sense, he's not, or something similar, right? And here the idea is that if meaning is determined by use, and it seems that, and if it seems that competent speakers show some symmetry in the use towards Tim Williamson is thin and Tim Williamson is not thin, it is at least difficult to understand how the semantics can make a difference, right? And say, no, one is true and the other is true, okay? So if there is a perfect symmetry in use, how is it possible that there is an asymmetry in the truth value? So it looks like borderline cases are challenging the principle of bivalence. The second aspect of vagueness that is very much discussed is the Schleicher's paradox. So a girl 1 second after her birth is a baby. Looks literal. If a girl X seconds after birth is a baby, X plus 1 seconds after is still a baby, looks super plausible. Some people might say, not as clear as the first one. Well, a consequence in classical logic is that a 12-year-old girl is baby, which is clearly false. So we have a proper paradox here. And so seemingly true premises, seemingly valid argument, seemingly false. Okay. Now the argument is classically valid, so we can reach the conclusion by enough instantiations of a second premise and more exponents. And further, in classical logic, we have that contraposition is valid, right? In the sense that if A, B implies C, then A negation C implies not B. And this means in particular that by contraposition, the validity of this argument tells us that there is a magic moment. So there is a moment where a girl with n seconds after birth is a baby, and the second after is no longer a baby. It's a kind of miracle, right? So that is the paradox. Now, vagueness seems to be related to some sort of indeterminacy, like in the case of Williamson. So it looks like indeterminate somehow whether Tim Williamson is thin. In the case of the Schleicher's paradox, perhaps the second premise, perhaps some of the instances, at least of the second premises, can be somehow affected by the expressions. And there are at least two ways in which we can understand the indeterminacy related to vagueness. The first one is the epistemic sense. So Tim Williamson is thin, is true or false, and not both, although we don't know, and presumably we will never know which, right? So the idea here is that at the semantic level, there is a perfect determinacy about the truth value of the sentence, but for vagueness related reasons, we don't have access to this fact of the world, right? And the semantic sense, what tells you is that Tim Williamson is thin. So in borderline cases, predications are not simply true or false, let's say. So the truth value of the sentence is somehow affected by the vagueness of the expressions. So the epistemicist will tell you, you see, this used to happen when I was doing the PhD. It was like the worst thing of the world being an epistemicist, but these days a lot of people hold this view. So the epistemicist says that there is a fact about Tim Williamson about which we are ignorant about, and also that in the case of the Sorites paradox, we are ignorant about the magic moment. Okay, so there is a magic moment, we don't know where it is, right? While the supervaluationist holds that there is no ignorance in borderline cases, in the sense that there is nothing to be ignored, right? So that there is no fact, we don't have knowledge, but there is nothing to be known, right? And for the same reasons, there is no ignorance about the magic moment. Now, the informal idea of supervaluationism is the following. So suppose that you have here like a Sorites series of from not told to told people. The idea is that a vague predicate can be made precise in different ways, and the use we make of the predicate does not select or does not point out to any particular way of making precise, right? A precisification is a way of making precise all the expressions of the language, right? So that in each precisification, each proposition, no matter the vagueness of their expressions, in each precisification, each proposition gets a truth value, true or false, right? And now the idea of the supervaluationist is that there are different ways of making precise the predicates, and we will say that the sentence is true exactly when it is true in all ways of making precise, right? So that, for example, this guy here, I think I call him Jonathan is here. Yeah. So John is told is super false because it doesn't matter which way of making precise the predicate you select, the sentence will count as false. Okay, and Dave, he is told because it doesn't matter. So it is true that he is told for every way of making precise the predicate. But the case of James is different because James, so there are ways of making precise the predicate that makes James is told false, and others that makes James is told true. And therefore, it is neither super true nor super false that James is told. Okay. Now, one thing that is like the most controversial part of supervaluationism is the issue about penumbral connections. I say that is the most controversial part because defenders of supervaluationism, they say this is the best argument for supervaluationism, and how do you say detractors? Detractors? Okay. So the detractors say this is the best argument against supervaluation. Okay. So the idea is that a precisification is a way of making precise all the expressions of the language, but these ways of making precise must be coordinated in the appropriate way, okay? They should respect some rules. Well, as a consequence of the precisification story, we have that classical tautologies will come true in any interpretation automatically. So consider Anne is a baby or Anne is not a baby. Well, each precisification is going to make true one side of the disjunction, even if Anne is a borderline case of a baby. So the idea is that even if Anne is a baby, is not super true, not super false, and so is Anne is not a baby, the disjunction will come out super true, right? Now assume that Carmen is 1 second older than Anne. Then the sentence, if Carmen is a baby, then Anne is a baby, this sentence must be true because any way of making precise the predicate that counts Anne as a baby should count Carmen as well, okay? So let's say precisification should respect comparative relations between adjectives. And well, this is the best example I could figure out. I don't know if it is very convincing, but if the glass is blue, suppose that you have a glass that is borderline blue and borderline colorless. And the idea is that any precisification that counts the glass as blue cannot count it simultaneously as colorless, right? So you have that the conditional, if the glass is blue, then the glass is not colorless. This conditional is true even if the glass is borderline blue and borderline colorless, okay? Sounds like plausible. Okay, so before starting with the more formal explanation of supervaluationism, so two remarks that I think are or can be interesting to remind. It is usual, well, it is not usual. Actually, Kit Fine says in his classic paper that supervaluationism makes a difference to truth, but not to logic. And some defenders of supervaluationism say, no, look, this is as close as you can get to classical logic, etc. Now, actually, at least in the context of vagueness, the point where supervaluationism coincides with classical logic is rather limited. So it holds when you don't have modalities in your language and you are considering the set formula structure. So arguments with sets of premises, but not with sets of conclusions, but only single conclusions. Okay. Now the reason is basically in the case of a modal language, supervaluationism does not coincide. Well, coinciding with classical logic and modal language is a very loose way of talking. Basically, it doesn't coincide with the local definition characteristic of modal logics, because for the supervaluationist, the inference, the box intro rule is valid, okay? And the reason why supervaluationism does not coincide with classical logic in the set formula, set framework, is because classically you have that a disjunction implies the truth of each disjunct, but this doesn't happen in the case of supervaluations. Okay, yes.
Also, in the meta differential, it's also it does not coincide with
I'm not sure why. So how? Yeah, I'm not completely sure, so I will need to. But okay, this is probably right. Thank you. So I didn't think about this, so I don't want to say. No, but we can work it out. Thank you. Okay, so suppose that you have a language with modalities. Supervaluationist interpretation is actually a modal interpretation. And the idea is that here our set of worlds is our set of precisifications, right? Now we will say that a formula is super true when in an interpretation, when it is true in every world of that interpretation. Now, if we go back to our definition of logical consequence in normal model logics, this was telling us that an argument is valid just in case for every interpretation and world in that interpretation, if the premises hold in W, then the conclusion holds in W. And this clearly is not a definition preserving the notion of super truth. It is supposed to be the central, the key notion of the supervaluationist semantics. I mean, if you look at supervaluationist semantics, the only characteristic thing of this theory is the idea that truth is not truth in a world, but truth in every world. So this motivates the definition of global consequence. Oops, it's right G here, right? I'm sorry. Yep. Yes.
When you work H2, yes. Can you dispense the accessibility relations, or are you working with a family of logics that you will obtain an extension by imposing restriction on?
So the discussion about supervaluationism sometimes focus on a language without modality, sometimes focus on a language with modalities. If you are talking about supervaluationism without modalities, then you can dispense of the accessibility relation.
And say that when you work with a structure that is appear, words and evaluations.
So the role of the accessibility relation has to do with the modalities, of course. And in the context of supervaluationism, the box means something like it is definite. Okay, it is definitely the case that blah blah blah. But it is interesting to think about which properties should the accessibility relation have in this context. Presumably, if something is definite, then it is the case, right? So accessibility should at least be reflexive.
Okay.
Now, should it be the case that what it is definitely, you might run into paradoxes of high order vagrants. Okay, so S5, in the case of S5 forbids second order vagrants. So the idea is that So if I'm not wrong, this is unsatisfiable in KB5, right? But the idea is that this is telling you that the Williamson is still, it is neither definitely that Tim Williamson is definitely thin. It's not definitely that. So the idea is the proposition that Tim Williamson is definitely thin is neither definitely nor definitely not. Right? So here the idea is that it is definitely that Tim Williamson is thin. This is borderline, right? So this will be second order values. And it is not clear that the for action is compatible with higher order values.
The
Transmissibility, it is not clear. Williamson says that it is not.
Yeah, because it allows to go from the one box to two or one.
To any boxes.
Yes.
Yeah, but for example, Diana Rachman, Susan Booksen is a philosopher in Oxford. She argues that the axiom 4 must be endorsed, even in the presence of infinite higher order values. So it is controversial. Williamson certainly he cannot endorse the transmissibility action, but this has to do with his particular way of explaining ignorance and vulnerabilities and the market for errors that he uses. So the idea is you cannot accept the local node
because it's preserving truth in a world, and this is not the notion of truth for the supervaluation. Is you should go for the global notion. Actually, I hold something intermediate between the local and the global, but it's another story. So how to adapt the trees for the supervaluationist logic? We had trees for the local consequence, and the idea is, well, working out some way of connecting the local trees with the trees for supervaluationists. Now we have this very direct and nice connection, which tells you that an argument is globally valid just in case the result of boxing all premises and conclusions with a universal box is locally valid. It's simple, but it works fine. Actually, I'm very proud of this. This was my bit in my PhD thesis. Okay, so once you have this connection between global consequence and local consequence, the idea is, okay, I'm gonna write my trees departing from this list with premises boxed and the boxed conclusions with a negation, right? And there we go. So for example, that P disjunction Q does not globally imply P comma Q can be shown via trees departing from universal box P disjunction Q, negation box U P, negation box U Q. And the key step here is that each negated box here is gonna give you different worlds, right? And so then we discharge this universal box in all these three, and we have an open tree, right? Yes. So we have an open path, and the counterexample basically is telling you that Q Q is true in W1 and P is true in W2, and negation P holds in W1, negation Q in W2. So you have that the disjunction is true here because of Q, it is true here because of P, and here because of P, but neither part of the disjunction is super true, right? Nice trick. Now we can use also the same tricks to show that the box introduction rule is globally valid, right? So we depart from box U and the premise, negation box U and the conclusion. This negated box leads you here. Now this new negated box leads you here. So we have negation A in 1. I forgot to add this. I had to add it afterwards. That super lazy, like go back to the code and write everything. No way. And then since we have a box here for the premise, we can extend the tree with this node and we get the contradiction. Okay. So what is the answer of supervaluationism to both challenges of vagueness, borderline cases, and the Sorites paradox? In the case of borderline cases, the idea was that how can there be an asymmetry at the semantic level when there is symmetry in use? And what the supervaluationist tells you is that, well, actually in borderline cases, propositions are neither super true nor super false. So there is symmetry, right? So if Tim Williamson, if Tim is a borderline case of the predicate thin, then neither it nor its negation is super true or super false. And this is compatible in the case of supervaluationism with the validity of the law of excluded middle, because we already know that the fact that the disjunction is true does not imply that some member of the disjunction is true, right? So the law of excluded middle in the context of a non-truth functional semantics does not imply bivalence. It is kind of nice. So they make this difference between excluded middle and bivalence. And in the case of the Sorites paradox, so actually if you remember, for the non-modal language and set formula structure, we have that supervaluationism and classical logic coincide. So actually this argument, which is valid in classical logic, must be valid also for the supervaluationist, right? So the fact that someone with 1 second is a baby and someone with 12 years is not a baby implies that there is a magic moment. So the supervaluationist is somehow committed to the magic moment, right? But now the thing is that although the supervaluationist is committed to the the existential generalization, she is not committed to any of the instances. Why? Well, you can see this in a perhaps a bit cheap way, but very illustrative. So you can understand that the existential generalization is a general disjunction of all the instances, right? So the supervaluationist holds that the existential generalization holds, so the disjunction holds, but in this case, this does not imply any separated by commas, any of the instances, okay? I think that's it. And we can, yeah, I'm gonna give some discussion about this. Is a bit, I wouldn't say it is proof theoretic, but it has to do with proof theory, let's say. which is one way to give a proof system for supervaluatory consequence out of a proof system for local consequence. Okay? And it's rather general. So the idea here is that since I have very little idea about proof systems in model logic, well, this is for another. I just assume that there is something like a proof system for the local consequence, and I give you the recipe to construct the proof system for the local consequence. Now, the motivation for this is, well, I mean, I think the trees work fine. I love them. I think they are completely fine. But many people will find the idea that in your proofs you are using accessibility relations and expressions that are not already in the language a bit annoying. Okay? So some purists will say, no, look, you have to give me a proof system where you use just the things that are in the language. Okay. So suppose that you have a proof system of this sort. There is a small theorem that shows you that adding the rule of box introduction will there is a trick here, but I'm going to tell you unless you discover it. So adding the rule of box introduction will give you a complete system for global functions. Okay. And well, the nice thing of this small theorem is that we have to prove first one theorem very characteristic of model semantics, which is the generated submodel theorem. Okay, so we will see that two words, W and W dagger, are connected when there is a finite chain of accessibility relations that brings you from one to the other, right? So the idea is that W is connected, is connected to W dagger when W has access to a world, that has access to a world, that has access to a world, and eventually in a finite number of steps, you get to W. Given an interpretation WR V and a world W0 in the set of worlds, the submodel generated by W0 is the interpretation where W dagger is W plus all the worlds that are connected to W0. And the accessibility relation and the interpretation function are the restrictions of R and V to this new And the lemma tells you that for any interpretation, the submodel generated by world W0 is such that formulas, is such that for any W, the formulas will get the same truth values, right? So the idea is that this W must be W dagger, but the truth value of this formula in W and the truth value of this formula in W, once we solve the non-connected words, get the same truth value. Actually, I'm not gonna prove this here because it's rather long, but there is a very nice book where you can read the proof. It's Spanish. Okay, so but I mean, it might be a bit cumbersome at some points, but it's rather accessible. Now,
So we will suppose that we have our generated submodel theorem under our belt and make use of it in order to prove the following connection. So B is a global consequence of a set of premises in one region. Just in case, B is a local consequence of the set containing all these A's plus all these A's with one box plus all these A's with two boxes or an arbitrarily big number of boxes, right? So the idea is that the effect of the global condition in the logical in the definition of the consequence relation can be achieved. So you can get the local condition, but suppose that the premises are as definitely or as both as zero. Clear, right? So suppose that the argument is not globally valid, then there is an interpretation. See. Okay, so there is an interpretation such that the premises take value 1 in every world in that interpretation, and the conclusion takes value 0 in at least 1. Okay, so a global counterexample is the premises take value 1 everywhere, the conclusion takes value 0 at the idea is that all that world W dagger. And now consider what happens in W dagger with the formulas, with the premises, with many boxes, right? Now, in W dagger, in order for a formula of this sort to be enforced, you will need a world W star, which is accessible. So it's connected to W dagger in I numbers of the accessibility relation, and where A is 0, right? Now we say that the A's are true everywhere, so there is no such world. So this guarantees that the result of boxing as many times as you like the premises locally absorbed. This is not right. Okay? So this is a counterexample, the same interpretation, taking as a witness the world where the conclusion is false, that interpretation gives you a local context. And for the other direction, we use the generated submodel theorem. So suppose that B is not a consequence of the result of boxing as many times as you like the premises, then there is an interpretation with a world where the result of boxing the premises takes value 1 and the conclusion takes value 0. And here the intuitive idea is very simple. So the only way in which this model might fail to be a global counter model to the argument is by having some world where the premises are false, right? So the premises, having some world where the premises are not super true. Now, this world cannot be connected to W prime because otherwise W prime via these infinitely many boxes will have access to that world, right? So this world must be the only way in which this interpretation might fail to be a global counterexample in the global sense is by having some world where the premises have fall, to this world is not connected to W prime. And we know that the generated submodel guarantees that if we chop this interpretation and get rid of these worlds, then we'll have a global counter model to be here. Okay. 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 Suppose that we have a proof system. Sorry. Suppose that we have a proof system for the local cost. When I say suppose, I don't mean, I just mean something that is somehow complete for local consequence, let's say for a KT or KT4 or whatever. Right? Now I request that this system has at least these two properties, which are according to reflexivity. The idea is that from set of premises, you can always derive one of these guys here. And we have form of the Tableaux that tells me that if from A1 Bn you can derive C, and from B1 to Bn you can derive each of the premises, then from B1 to Bn you can derive S. Okay? Now the idea is that for any such system, if we add this rule of a box introduction, then the resulting system is complete with respect to the global notion of value. And what is the argument? The argument is the following. Suppose that an argument is globally bounded. What we want to show is that this system is such that there is a global, okay? So by theorem, the previous theorem, we know that the result of boxing all the formulas and the premises locally implies, right? So our previous result told us that if this is valid, just in case the result of boxing all the premises locally imply. Now we assume that our proof system was complete for the local notion, so there must be a local proof for this. And since we define our global system by the addition of rules to the local system, that is, any local proof is a global proof. The fact that this is local valid, so that there is a local proof, guarantees that there is a global in our system. Okay. Now, what we need to show is that there is a global proof, but from the edge without the boxes. So we have to get rid of the boxes, and we can do it via reflexivity and cut. So basically, by reflexivity, we know that any premise here in the argument can be derived globally. Then we can apply box introduction, and actually we can apply box introduction as many times as we want until we reach the number of boxes that we need in order to write this proof here. And we can do this for each element of A. So we can, with the result of this reflexivity and box introduction process, we can like feed the platform in order to show that actually we have a global proof from A1 AM to